webinar, and we will automatically mute everybody in the audience to avoid background noise. Questions can either be submitted during the talk in the chat, or after the presentation from Sylvie, we open the audio channel so you can directly ask her verbally. If you have, meanwhile, any technical issue, feel free to go back to our virtual audio, lobby, and we will try to help you. So I have impression quite a bunch of you already know her, so let me introduce our today's speaker. It's Ms. Sylvie Bosch-Charpenay, Applications Engineering Manager of the Process and Environmental Analysis Solution Divisions from MKS. And Sylvie will present us the use of the FTIR in the thermal analysis of the lithium-ion battery testing. I hope I pronounced it somehow correct, Sylvie.
Yeah, that's okay. Yeah.
Okay, so the audience is yours.
Okay, thank you guys. Thank you, everyone. I'm glad. We have a very wide audience today. Today I'm going to show you some data and application that we've done in the past year and a half, maybe, that has to do with the battery thermal runaway of lithium-ion batteries. So we will cover a background first on those fire issues that can occur, and this would be both for cases for car batteries as well as data centers batteries. I think there's a broad interest from very different sides. I'm not an expert on the lithium-ion battery chemistry. However, doing some searches, we did look through and looked at the gases that can come out from a chemistry perspective. And so we've applied FTIR, our MultiGas, which most of you hopefully know. So the MultiGas is used a lot for emissions, for engine emissions, car emissions, but it's also used, it also has a very broad applicability for many other applications. And one of them is fire analysis. And the advantage of FTIR is that are the same as what we use for engine emissions, is that it's fast, it can measure in real time, and it measure a large number of gases, in particular gases that you guys might, for the ones who are more familiar with emissions, might not be as familiar with, but these are gases like HF or HCl, like acid gases, and then others. So the type of gases that are important here are a little different, but it's still the same analyzer, same principle. So I'll go through a little bit on the principles of FTIR absorption spectroscopy, just as a explanation of what we've done in the past, just because we have such a wide variation of application in that our customers are doing. Some were done with a fire that that was put on a truck cab that was set on fire, and for which we had taken measurements. So also we'll go through on how battery fire is different. Testing is different from materials fire analysis, gases that can be measured, and then importantly the configuration on the instruments and sampling configurations. And then some advantages of the MultiGas versus other FTIRs in summary. Okay, so lithium-ion battery fires can be an issue where there is, because it could be due to external heating, to an external fire, could also be due to a battery defect, which makes the battery start heating up more and more and essentially becoming out of control. This was more of an issue, I think, in this was like 4 or 5 years ago when there were certain cell phones that were not allowed on planes, if you remember, because they had certain issues. And that's why there's been a lot of R&D in order to determine the behavior of battery under stress, whether it's internal and also quality control. Improper cooling and thermal management could be also a cause. And what happens is that you have some gas that's released and being vented, and some of these gases being flammable or corrosive or toxic. So if you think of a battery, there's a lot of energy in a battery that's stored in the form of chemistry, of chemicals, and then when those get released in the form of gas, there's a large amount of gas that gets released pretty quickly, and that can turn into gas ignition, explosion, or fire. So that's why there's a lot of work that's being done. So I've put in a resource here of an article if you guys are interested, because this is all from that article, that information that we got here. So the battery design is essentially critical to mitigate those issues. Some fire retardants in some cases contains fluorine, which is not good because it can produce HF. In some cases, the fire might actually be beneficial because you get a worse gas release if there's no fire. And the fire testing, battery fire testing that people can do provides feedback for improving the battery design. So the main gases that are in a battery, the main component that are in a battery, and they're not gas, they're all more like liquid or solid actually phase, is the electrolyte. So the electrolyte is typically like lithium hexafluorophosphate salt that's dissolved in a mixture of alkyl carbonate solvents. I'm not a chemist, so I might not pronounce those names very well, but we have seen that there are carbonates like ethylene carbonate, dimethyl, diethyl, and ethylmethyl carbonates. And I'm going to refer to them as EC, DMC, DEC, EMC, because this is shorter and easier. So those are really the main components that are inside the battery. And then when that electrolyte is decomposing, obviously it will adversely affects the performance of the battery, and it can lead to catastrophic failures. And the gases that are released during those thermal decomposition are really gases that we're all very familiar about, like the CO2, CO, hydrogen, which we cannot measure, but this is also released. Ethylene and HF, or the trace compounds that can be present as well. And those fluoroorganics, some fluoroorganics, and also unstable phosphorus-based PF5 and POF3, which typically we have not seen in very large quantities, but because they're unstable, but that can be present as well. So as I was alluding earlier, FTIR has been widely used for fire analysis, and the advantage is, compared to a GC, that the FTIR could provide continuous gas measurements live during an event. Many gases are measured simultaneously, and there are ISO standards. There are many standards that are being used, which specify requirements, recommendations on sampling parameters, and guidelines for use of the FTIR instrument itself. And some example of use here are like for upholstery material testing, for materials that can go in really moving vehicles typically, because that's where it can be the most dangerous. And there is also a test method, an NCCA UL test method that is used to evaluate thermal runaway in really battery, specifically for battery energy storage systems, and where they specifically request the use of FTIR with a minimum resolution and a path length of at least 2 meters, which both requirements that we easily meet with the MultiGas FTIR from MKS. So a brief introduction to our analyzer that I'm sure many of you know. It is field-proven rugged and includes preheated lines and integrated pressure sensor, and it's designed to measure hot and wet streams, which is particularly suited for fire conditions. And we measure many acid gases like HF, HCl, or HBr, or HCN. These are the ones that can be potentially produced. We have different path length detector options, 5 meter, 35 centimeter, 2 centimeter, and we both have liquid nitrogen cooled detectors or thermoelectric cooled detectors, which we call TE, thermoelectric cooled, and those which do not require liquid nitrogen cooling of the detector and can be used 24/7. So depending on what the customer need, we offer either option. Large calibration library, and we have many recipes for many different applications. So this is the test I was mentioning earlier. This was in the middle of nowhere in California a few years back, where we had some trucks that were set on fire, and we had placed a probe that was placed in the cab of the truck, and that was connected to an FTIR that was placed a little further away, obviously at a safe distance, and the trucks were set on fire. We had created an enclosure to protect the FTIR, mostly from dirt and whatever else that was around, and then we had measured the gases that were produced during the fire. And there was a lot in that test. There was a lot of HCl, HF, essentially produced from the burning of many parts inside the cab over here. So for battery testing, we can measure lots of gases. This shows all the gases that we have added to our recipe. The main ones I've highlighted in red, because these are the main ones that people have been mostly interested about. And So we have obviously ambient gases, nitrogen gases, acid, VOCs, the carbonates, and then toxic gases. That includes also, sulfuric acid, and then ethylene oxide, propylene oxide, HCN. These are obviously particularly toxic. Obviously, those are toxic as well. If you look and compare how different the battery fire testing is from material fire testing, there is, in the case of a battery fire, if it's really a fire, there's a large amount of gas that can be released in a short amount of time, as opposed to possibly more progressive gas release for standard fire testing. So if you think of, in the battery where everything is in a solid phase, if things are going to be released quickly into a gas phase, that means there's going to be percent level of gas that's produced quickly. And so depending on the sampling conditions, either the straight sample gas or gas diluted with ambient air can be analyzed, because if you have a lot of percent level of gas, it might absorb completely in the infrared with the gas cell chosen, and in that case, you would only see partial information. So in both cases, there's likely to have a complex gas composition, and then you really want to check what the path lengths, in order to avoid saturation, that you're going to use, either path length or dilution. So a little bit of background on FTIR absorption spectroscopy. So FTIR measures absorbance, and the absorbance features are gas specific, as you could see on the right. And here, these are the absorbance features of all the of many different gases. So this is the power of FTIR. The absorbance is proportional to the number of molecules in the line path times the path length. So if you look, our standard gas cell here is a 5 meter with a folded path. And so if you have a sample in here, in your gas cell over here, and then you have an infrared beam that shines through the gas cell, because there's a folded path, a long path length, the light is going to go through all this sample and then get absorbed, partially absorbed, and you're going to be left with obviously much less light in the outcoming beam, and that's where you get your absorbance. So if in here the concentration is fairly low, but the path length is high, you're going to get a certain absorbance. And that same absorbance can be achieved, so you could see with the IR beam and the same level coming out, with a gas cell that's much smaller, but with a higher concentration. So in here, what's important is the product of the gas cell path length times concentration. And so you get the same absorbance if you have this configuration versus this one. And so in our case, in here, what we often see, if people use this configuration, which a lot of people have as a standard, and then they measure percent level of the gases that come out, then they might have issue. It's not a problem if only CO2 or water is at percent level, because those have very sharp absorption peaks and they are very localized. But if you have ethylene that's at percent level, that whole region here is going to be fully absorbed. And that means you cannot measure anything in that region anymore. And so you essentially, by having percent level of hydrocarbons, you're really hiding full regions, which makes the analysis more difficult. So this is in here the additional thing people need to worry about in terms of whether to dilute or not, or to use a path length that's a 2 centimeter versus a 5 meter. So just to show you what happens with percent level concentration that occurs during a thermal runaway, if you use a regular 5 meter cell and you're really measuring at the height of the gas release, you're gonna get the spectrum in purple in here, where essentially everything here is absorbed, and that's the absorbance. Anything really above 2 is unusable from our perspective. Even above 1.5 is not going to be usable. So all this region here, all this is totally absorbed, and the data cannot be used. If you dilute or you use a smaller path length, then you're getting this spectrum here in green, where you could see, there's the carbonate peaks, the ethylene peaks, and you still in here get to see the CO2, and so you have all that access to all that information. So this provides an appropriate path length for the concentration or appropriate dilution. Because earlier on, we had customers essentially measuring, and they were using a recipe, and they were like, the results are very strange. And that's because really everything was saturated. So to reiterate, during the battery thermal runaway, several liters of gas will be produced with percent level concentration, and they're going to be produced quickly. So the FTIR is going to be great, measuring at fast time resolution. And from a test perspective, you can either place the pump before or after the FTIR, or you can essentially have a setup, automated setup, as what is used a lot in Germany and Austria. And obviously you still need heated lines before the analyzer to ensure there's no condensation. And then these are your two options, where here you measure with a 2 centimeter gas cell, or you use with a 5 meter cell, but you have some dilution that's happening in your sampling. So this is an example of analysis software that we have. We have something that's called the gas search utility, that in here I showed, where it shows all the gases that were seen during that test, and you could see that there's obviously large amount of CO2, of the carbonate, COS, two different kinds of carbonates, some kind of oil. Good news is that there were low level or none of things that are more dangerous, like sulfuric acid. This here shows how, in here, this little utility shows how we have a good match between the measured and the predicted absorbance throughout the whole spectrum. So in here, it's really from 1200 to 500 rather, to like 5,000 wave numbers. So you could see we've really represented and captured all the absorption features, which tells you that there's nothing else that has not been accounted. Unfortunately, we could not show so much data because a lot of it is proprietary. But in here, this is what we have seen for a few data points that we were able to get from customers, where you could see, there's some significant formaldehyde release. HF was luckily all on the very low side. CO can get really high at some points in the height of the release, same as ethylene, and then the carbonate as well. And there's really a complex chemistry that changes with time. You could see that, all these gases, if you were to overlap them, really things happen at different times. So having the ability to see when things come out, helps in understanding the decomposition chemistry. So if you compare FTIR compared to others, well, we have a wide range of gas cells that can be used, and so that you can decide to run your sample with or without dilution. We run at 5 Hertz. We have high resolution, and we have recipes and calibrations for all these gases, all these acid and toxic gases, transferable calibrations, so that all instruments can use the same calibrations, and the user does not need to create calibrations. We provide recipes. And we also have a ready-to-use battery testing application package, which includes all those components, and that also includes the gas search utility software. So in summary, the lithium-ion battery fire testing has become increasingly common in the last year and a half. FTIR spectroscopy instruments are ideal to measure those release from fires, and the MultiGas is well positioned to address that market, because of all its features. So this is what I have for today.
Sylvie, many thanks. Any questions from the audience? Let me first ask you something, since I'm not aware of it's possible. The replacement of a gas cell, is it possible to do it in the field, or has the unit to be shipped back to the factory for recalibration purpose or something like that?
It can be done in the field.
Okay, great.
It's not a, you need to have some familiarity with the instrument, but it's really, a lot of your users know how to, remove the gas cell to clean mirrors and whatever else. And this is essentially replacing the cell, the 5-meter cell with the 2-centimeter cell, or vice versa. And but there might be a little bit of alignment of the turning mirrors to optimize, but it typically is for customers who know how to remove gas cells. It's not a big deal.
Okay. In case you don't like to speak into the microphone, please use as well the chat. I mean, I'm open to read the news for Sylvie. And the second topic which popped during your presentation in my head is, an infrared spectrometer is somehow sensitive to gas, and fire by its nature is not a cold gas. Is there a kind of cooling down the gas necessary, or can the probe directly taken from a source and inserted into the gas cell of the gas?
That's a good point. This is all sampling, obviously issues. The all depends on how much distance you might have between the where you do the sampling and where the analyzer is. When the gas is in the analyzer, it's going to be at 191. If the gas was much hotter, it might end up being hotter in the MultiGas, but typically the volume of the energy contained in the gas is going to be smaller than the heating energy of the gas cell and the heated lines. So it's going to still be at a temperature close to 191. But there's definitely more sampling challenges for those applications that the customer or the integrator has to address to make sure that it's appropriately, that temperature and pressure of the gas is what we expect it to be for it to be analyzed correctly.
Mm-hmm. Okay, got it. Thanks. Any further questions?
Yeah, I would have a question along those lines. This is Aaron Varga from BMW Group. What about particles in the gas stream? So a thermal runaway from a battery contains a lot of powders and solid material. Would you have to put very, very good filters in between?
Yes, yeah. You certainly don't want to have any particulate getting into the gas cell of the analyzer.
Mm-hmm.
Same as what you would do, for an emission test where you want to have filtering, because particulates are gonna dirty your gas cell mirrors, and then you're gonna lose signal and have to clean it. So yes, the filtering, the sampling is what is in here needs to be carefully designed.
Mm-hmm. And maybe one follow-up question, if I may, and that's about the reaction, the reaction rate of the gases that are piped from the source. So we have a certain amount of reactive gases like carbon monoxide that are emitted, and then they travel a certain distance and a certain time to the analyzer. Have you done any research on how fast-lived components may be detected, or what the optimal travel distance is between the source and the detector?
Between the fire source and the instrument.
Right.
Yeah.
Right.
So that might be things that our customers are working on. We have not been very exposed to that. I think in terms of safety, what would be more important is determining what would be a safe distance to that people might be exposed to. People might not be, and again, this is really like fire testing sampling details that might depend situation to situation. But in here it would be a test that customer could certainly do, try to see at different distances how much the chemistry can change. Things like CO or most of the species that we see are not gonna change significantly in a few in a few seconds or minute that it will get to the analyzer. Certainly things that are like the PO5 and those ones we have seen will, because they are very reactive species, and that would be. I think there might also be a lot of difference, from run to run. It's not like an emission, of an engine where it's really repeatable, reproducible. There might be a lot of other parameters that really influence the way the fire or the decomposition is occurring, from even run to run. So that's where people are doing research.
Mm-hmm. Yeah, thank you very much.
Yeah. So for acid gases, our analyzer is designed to measure ppm or high ppm levels of acid gases. The MultiGas, as long as the gas is in the gas phase, there is no deposition on the mirrors. Where you get in trouble is if you have particulates, or if you have liquids, if you have something that might condense on the mirrors or the gas cells. At 191, there's very few gases that can condense. The main one that we've had trouble with is sulfuric acid, H2SO4, and that one is very tricky, because the chemistry of sulfuric acid, if there is a little bit of water, it's a complicated chemistry. So in some cases, we've seen that if there is sulfuric acid in the stream, in the gas phase, if there's a little bit of water, or if the temperature or pressure conditions are such that it starts to get into mist, and this can condense in the mirrors even at 191, then we've seen degradation of mirrors. But HF, HCl, HCN, all of those, they are in gas phase, and it's not a problem for the analyzer. Sulfuric acid, fortunately, we have not seen in battery. Obviously, battery makers are probably very aware that they want to avoid any path length where sulfuric acid can be produced, because that would be very bad. And we have not seen it, but I'm sure that's part of what the R&D that people are doing.
More questions to come? Sylvia, I think that's it.
Excellent.
Once more, many thanks. Hope everybody enjoyed the talk. I thought it was very interesting topic, especially with the upcoming investments in battery production in Europe. So yeah, again, many thanks. And
don't hesitate to reach out to us
if you need see everybody again in a month from now. Yeah.
Okay. Bye. Thank you all.
Thank you.
Thank you. Bye-bye.
Thank you.
Bye.
Thank you. Bye.
Thank you. Bye-bye.
Thank you.
Bye-bye.